So let's look over this agenda very quickly. The spring constant, determining a spring constant gizmo, which is based on Hooke's law, is due tonight. You're just turning in the student exploration sheet. The assessment that was online is just for your own review. So just turning in the student exploration sheet as one document, preferably PDF form, and putting that up on Access before midnight tonight Pacific time. And then today we're going to spend some time, probably about 25 minutes or so, reviewing tension and Atwood Machine's problems. And I'm also going to take a few minutes before that to show you the Atwood Machine I have set up in the back. So on the other camera that I have here, you can kind of see that. And then we're going to talk about a group assignment. It would have been more of a lab, hands-on kind of a group assignment if we were here, but we're going to use a gizmo. So this, just like the determining a spring constant gizmo you're turning in tonight, we're going to do one, but have you work on it in groups today in breakout rooms. And we'll do the same thing. You'll go to Explore Learning, you'll log in, you'll open up the gizmo, and you'll work in groups of 2 or 3 and turn that in. Looks like we just lost somebody. If you are able to stay logged in, then you'll work with the group, and as long as you're able to stay logged in reasonably consistently, you'll work with the group, and then just one person from each group will turn in their student exploration sheet. So you'll probably all fill your own out and think it through and work it through, but you'll just choose one person from the group to submit it. That'll be due Thursday night. For international students watching the video, if you want to try to coordinate with other international students, you guys did that last semester, that's fine, you can do that again. I don't want there to be more than 3 in a group, so either just with one other student or 2 other students. If you want to group together, you can, or you can do it on your own. It's not that it's impossible to do on your own, it's not really that complicated, but I do want to just kind of mix it up. In normal class setting, a couple times a semester, we'll do a lab where just one person from each group turns it in. So I want you to get as much of that normal feel as we can. So we're going to try that on this one, see how that works. Then I've also listed here what the next assignment will be, and it's not due till next Monday for you guys, next Tuesday for B-Day. And it is more work on positive physics. And this is reviewing back Unit 7 on systems. And so some of you may already have done some of this as you were preparing for the final. And if you've already got it done, you don't need to redo it. As long as your completion percentage is 100%, you'll have it done. You may want to review it a little bit, but going back to that Unit 7 systems chapter, you're going to be doing the work section again, and you'll be just doing 4 of the skills. They're actually the last 4 skills on the list. Free body diagram analysis, followed by vocab and concepts, followed by complete problems, followed by challenge. So it's just the bottom 4 skills listed on that site. You'll complete the work section and then submit a snapshot. This snapshot, though, will need to be of the dashboard, because if you just take that top right-hand corner of the screen, that only shows 1 skill. So for me to see all 4 of these skills, I'll need you to take a picture of the dashboard and make sure it's a big enough snapshot that I can see your name in the corner, and then all 4 of those skills percentages. It'll be based on completion again. So again, recommend that you go through it the best you can, do corrections as you go. Since it's the work section, you don't have to do any finalizing or anything. Just correct it as you go, and your grade will be based on percent completion. All right, so if you do everything, if you correct everything, you should get 100% on this assignment. I believe there's 35 questions. It's like 5 or 6 questions on free body diagram analysis, and like 15 or 16 on vocab and concepts, and then another 5 or 6 on complete problems part 3. And then I think there's 4 or 5 challenge problems, something like that. So it ends up being about 35 questions. And that'll be due next Monday for you, Tuesday for B-Day. All right. So any questions about what's coming up, when things are due? All it's on Access as well. So obviously you can look on Access and see when things are due. I did put this description for the positive physics telling you what to submit, which sections to do. It's also in the description of the assignment on Access. On the Atwood machine, it tells you one person submits it. So like everything I've said verbally here is also on Access in writing, but so if you're chopping in and out and having a hard time hearing, you can read those directions as well. Any questions? All right, let me pause on the picture here, the screen share, and I'm going to pin the other camera so you can hopefully see it a little bit better, the Atwood machine I have in the back. So I'm going to transition back here. If you look at the thumbnail, you can probably kind of see it, but let me see if I can get a little better view. All right, so on this Atwood machine, let me stand on this side. So it's a little bit of a glare with that light coming through. Oh, sorry, I pinned the wrong video too. That's not going to give you the best view. Let's try this one. There we go. That's better. So you can see one half of the Atwood machine here, and hopefully it's pretty clear on your screen. It looks pretty clear on mine, but if you look at the setup here, I've just anchored this to the table, and I only have it angled so that this won't hit the table or hit any of the bracing. That's the only reason. And then I just got a pulley up here. They call them frictionless pulleys. I guess their trade name is called super pulley because they're very low friction. I can show you one kind of in action here. I don't know how well you'll be able to see it on the screen, but when I spin it, it just spins and spins and spins, and seems like it goes forever. It hasn't even shown any signs of slowing down yet. Usually I pass this around the room and let you try it and just see how surprisingly little friction there actually is in this. I can see it starting to slow down now. It's just starting to slow down. And so they're very, very low friction pulleys and also very low mass. So I've got one here, and then I've got this string, and I've got a little plastic hanger at the bottom, and there's 20 grams hanging on here, and then the hanger itself is 5. So I've got 25 grams hanging from this string, and then the string goes up and over across the room. So we'll carry it across. You can see a little harder to see with that backlit window, but goes across the room. And then there's another identical setup on the other side of the room where, again, the super pulley mounted out so the string doesn't hit. And you can see right now that that weight over there is hanging just a little bit above table height. And then over here where I want you to focus your attention for now, also just a little bit above table height. All right, so they're nicely balanced. And what I want to show you is well, first let me remind you, I've said this before when we talked about this. On questions about Atwood machines, we talked about this before Christmas. They often will say the pulley is frictionless. And like you saw, it is very low friction. So we can ignore any friction effect. Even though it's not truly zero, we can ignore it. It's negligible. They'll also say you can not worry about the mass of the pulley. Okay, now, the mass of the pulley would matter if it had significant mass, because to get the pulley to turn, you're trying to get the pulley to go from motionless to having motion, which means you have to apply a force. In this case, it would actually be called a torque, which is something we're going to be studying here in about a month or so. And so we would be applying a force at a radius from the center, which is called a torque. And so we would need to apply a force to get this to spin, but if it's really low mass, that torque is also, like the friction, negligible. It's not that it doesn't exist, it's not truly zero, it's just small enough to ignore. Then they'll also often talk about a massless spring or a lightweight spring. Sometimes they don't specifically say the pulley is, that you can ignore the mass, they'll just say it's small. And so that's like keyword, you can ignore it. And the string, you can ignore the mass of the string. But I want to show you that in reality, the mass of the string does make a difference. So right now, they're about the same height, these two weights. So it stays balanced because we've got a balanced force scenario. This one's pulling down, that one's pulling down, they're pulling down with equal weight. Now, if I raise this up quite a bit and then I hold it still, if I hold it, I'm applying force to keep it there. But now on that side, that weight is much closer to the ground, so it has a lot more string hanging below the pulley. This only has this short little bit of string hanging below the pulley. Now, in the problems we're asked to solve, it says we can ignore that. But I want you to recognize here that we actually, so if I let go of this weight, you're going to see it slowly start to rise. And you saw that it was balanced before, and you saw that it didn't move anywhere, but when I unbalance the amount of string, the extra string on that side, the mass does matter, and it actually makes this accelerate upward. So let me get it balanced again so that it doesn't accelerate upward. And a couple things that hopefully helps you recognize. One, that the friction of the pulley is pretty low, because even just that little bit of extra string on the other side makes it move. And second, that the mass of the string, while we usually ignore it in problems, actually isn't something that can be ignored in reality. It actually does create a difference. The problem is you would have to use calculus to solve for it because it's an ever-changing amount. As the string gets longer, the mass gets gradually greater, but it's constantly changing. So we can't use linear algebra, we can't use regular algebra to solve that kind of relationship. So it takes more than what we have for this class. All right, now I want to show you one other thing, and it's a little bit harder to see unless I lower the angle. So I'm going to lower the angle so you can watch this go to the ground. I'm going to tap this. It's balanced right now. Let me raise it up just a little bit so it's mostly balanced, but so that will fall a little bit greater distance. I'm just going to tap this and apply a force, but I'm not going to apply a constant force. I'm just going to give it a little tug. Okay, so I give it a little tug, and you can see that the friction actually stopped it. Okay, so that proves there is some friction in there. It's not just a frictionless pulley. There is some friction. Now I'm going to come back up here and get it balanced again. I'm going to give it just a little bit more of a tug this time, and I want you to watch how it does fall. Yeah, it's a little bit hard to see, but try it one more time. Hopefully you can see that it's falling at a pretty constant velocity. I give it a little tug, but then once that tug is gone, then the force is no longer applied. So I'm accelerating it, but once the acceleration, because the force is gone, once the acceleration is diminished, it will continue to fall at a constant rate because of that weight over there. Now, if you watch really closely, it looks constant. Right towards the end, it maybe starts to speed up as the amount of string on this side increases. But it's pretty constant as it falls. It almost looks like something's wrong because we're so used to seeing something accelerate. Move it back a little bit. It won't angle any more than that. I don't know. It does a little bit. Let me try one more time so you can see it actually go all the way to the ground. So it looks like something's almost wrong as it's falling because it falls at a constant rate, and we're so used to seeing things that accelerate when they fall. So I wanted you to see a couple of things there. Any questions about any of that? All right, well, let's go back to the notes then, or back to the presentation that's going to allow me to do some notes. All right, and let me go ahead and stop sharing this video so I don't give you motion sickness. All right, so what we're going to do today to continue on that, so we started with a little visual demonstration of Atwood's machine. Now we're going to quickly review tension and what it means, and then we're going to talk about, or we're going to solve a problem about an Atwood machine similar to the one we saw before Christmas break. I'll show you the way this curriculum explains it, and then I'll remind you of the way I taught you before break of a systems approach. I think it's good to see different approaches at different times so that you can not just have the mentality that there's only one way to solve a problem. So let's start though with just a general concept of tension. On this next slide, it's going to give us some reminders about what tension means. Can I get a volunteer to read this slide for us?
Sure. When a cord, rope, or chain pulls on an object, it is said to be under tension, and the force it exerts is called the tension force, Ft. The tension force is the same throughout the cord, rope, or chain, which is assumed to be massless. Any object that is hanging or suspended is considered to have a tension acting upward. Any object that is pulled is considered to have a tension acting on it in the direction of the pull.
So again, you can say, you can read that it says, assume it's massless, but we just showed technically the mass does matter, but we're going to ignore that. And that it's going to be the same throughout. So whatever the tension is at one end of the rope, it's the same at the other end of the rope. All right, can I get someone else to read this next slide for us? It's a little bit shorter.
Yeah, I can do it. There is no special formula to find the force of tension. We need to use force diagrams and net force equations to solve for it.
All right, so there is an equation for friction force. Friction force equals coefficient of friction times normal. There is an equation for spring force, Hooke's law. Spring force equals the spring constant times however much the spring was displaced. So we have equations for certain kinds of forces. We're going to learn one next week, actually two next week. One's gravitational, one's electrical, and they're very similar. So we're going to learn those both next Monday. And those will be kind of the last specific force equations, but tension doesn't have one. We have to draw free body diagrams. We have to figure out the net force and then use our logic and understanding of net forces to solve for the tension. All right, so let's practice a couple. Let's do this one together here. Hopefully you can see here on the screen, it says a 25 kilogram lamp is hanging from a rope. What's the tension force being supplied by the rope? So the object is the lamp. So I'm going to draw a dot here. That's my lamp. Johnny, what's one force that would be acting on this lamp?
The force of gravity.
Force of gravity, yeah. Everything has weight, so that's a pretty safe bet. We know that we're going to be able to have that. Nat, how would I calculate the force of gravity or the weight of this lamp?
You would use Newton's law.
Okay, can you expound on that a little bit?
Oh, sorry. So you would take the weight times 9.8.
We're trying to find the weight, so it's not the weight. There's another similar word.
Oh, the mass, sorry.
Good, yeah. So we're finding the gravitational weight, so we're looking for mass times acceleration due to gravity. That's how we would calculate it. Good. Sally, what's another force acting on this lamp?
Friction.
There might be friction holding the knot or holding, yeah, I guess it'd be the knot or whatever is, however it's connected to the lamp, but it's just hanging from the ceiling, for instance. So I don't think that friction would be a part of actually acting on the lamp in this setting.
Okay.
Evan, you have any other ideas? Oh, you got another idea, Sally?
What would the tension just be the other one?
Yeah, there will be tension. So there's going to be the tension in the rope that's holding the lamp. There's going to be the weight of the lamp pulling down. Evan, would these two be balanced or will one be greater than the other?
They would be balanced.
And what draws you to that conclusion?
Because the lamp is not accelerating.
Okay, good. The lamp is not even moving, so it's not accelerating. If there's no acceleration, there's no net force. If there's no net force, the forces are balanced. So this tension force and this weight force must be congruent. So we can put little congruency markers on here to emphasize that. So if I can calculate the weight force, then that is the tension force, right? The tension force is the weight force. Make sense? So there's no set formula for tension. We have to think through, well, how does it compare to the other forces that are going on here? In this case, the only other force is the weight. So let's look at how they solved it here. They've said in the given part, we know the mass is 25 kilograms. We're trying to find the tension. We know the net force would be mass times acceleration, and it should be 0 because it's not going to be accelerating. We know the net force would also be the tension minus the weight, and that should also equal 0 because they have to be equal and opposite. So the tension has to equal the weight, and then the weight is 25 times 9.8, like I think Nat told us. And so we should get a weight force of 245 newtons, which is also the tension force. All right, let's try another one. There we go. In this second problem, we've got a crane lifting a 60 kilogram load at a constant velocity. Determine the tension force in the cable. So we're talking about one of those cranes that's got a cable hanging down, maybe it's got a big beam or a big pallet or something hanging on it. So that load, that pallet, that beam, whatever it happens to be, is what we're focusing in on. So here's our load, whatever is hanging from the crane. Andy, what's one of the forces on this load?
Would it be gravity?
Yeah, there's going to be weight. Everything has weight, right? So unless we're in a zero gravity scenario, so it's going to have weight, and that's still going to just be mg. So we know that. And we know the weight is 60, so 60 kilograms times 9.8 meters per second squared. All right, Ethan, what's another force?
The tension force going upward.
Okay, tension force going upward. All right, now this is not still. The lamp was just hanging there. This is not still. It's saying it's lifting this. So are these equal, or is something greater than or less than the other?
Tension's going to be greater.
Okay.
I think they're still equal because it's a constant velocity, no acceleration.
Okay, so here's the question, and here's the thing you have to stop and think about. Did there have to be a force to get this moving?
Yes.
Yes.
Yeah, at some point there had to be a force to get it moving, right? But here in this problem, it says right now it's moving at a constant velocity. So
So does
originally
that
there
mean
had
just-
to.
Does
Go
that
ahead.
mean you just like kind of ignore the force that was acting upon the object to get it to move?
Right, so anytime we draw a free body diagram, we're kind of taking a snapshot in time. We're saying at this instant, what's going on? And so at some point, they had to apply a force to get it to move. But right now, when we're drawing this free body diagram, it says constant velocity. Since constant velocity, it is moving at a constant velocity, the acceleration is 0. And if the acceleration is 0, the net force is 0 newtons. And if the net force is 0 newtons, then these have to be balanced. And it's basically the same mathematically as the previous question. Be okay with that? Making sense? All right. So the tricky part is on this kind of question, it's moving. So the first thought is, oh, to get it to move, we had to apply a force. But you have to really focus in on the wording of the question and not think about what happened in the whole scenario from the start to finish, but just what's happening right now. And right now it's going at a constant velocity. So right now there's no net force. All right, let's look at the next kind of question. A 90 kilogram climber rappels from the top of a cliff with a downward acceleration of 1 meter per second squared. Determine the tension in the climber's rope. All right, so first things first, we always want to start with our free body diagram. So I'm going to say the dot is climber. And what forces are acting on this climber? Rocky, give me one that's acting on this climber.
Weight force.
The weight force. Climber has weight. And that's going to be that due to gravity, gravitational force, mass times g. All right. Kyle, what's another force acting on this climber?
Tension force.
Tension force. Okay, that rope is holding the climber up, at least to some degree. Now, in this case, it says it's downward acceleration of 1 meter per second. So are these forces balanced or not?
They're not balanced.
Johnny, I see you shaking your head. I don't know who else spoke, but tell me what you're thinking there, Johnny.
They're not balanced because the climber is accelerating in a direction in the downwards direction, so therefore they can't be balanced.
Good. If there is an acceleration, that means there has to be a net force. And the acceleration is downward. So what's the direction of the net force? I see a couple pointing. Yeah, the net force and the acceleration always go in the same direction. Still trying to emphasize and hammer that point home. So the acceleration is down, therefore the net force is down. So Evan, which of these forces is lighter than the other, or not lighter, but which one's less than the other?
The tension force,
How do you know that?
because it's pulling up. So if it's less, then it will accelerate down.
Good. The force that's pulling down has to be greater for it to accelerate down, right? So the upward force must be less. So I've readjusted my diagram here to show this tension force up should be shorter if I want to represent what's going on, because it would only accelerate down if the weight is greater than the tension. Now, what if the rope broke? What would be the acceleration of the climber if the rope broke?
The acceleration now plus 9.81.
Close, close. And I like,
Just- It'd just be 9.8. It'd just be 9.81 meters per second squared, right?
yeah. So I think, Nat, probably what you're thinking is, if we wanted to find the velocity, we would have to know what the velocity is now, and then we would have to factor in the acceleration later to figure out however much the velocity increases later plus that original velocity. But the acceleration is just how rapidly is that person's velocity changing. So right now it's just changing by 1 meter per second every second. So they're not actually speeding up very much. They have a pretty slow acceleration. But if the rope broke, there's no force holding them up again. So now it's just going to be pure free fall. So the acceleration doesn't tell us much about the velocity itself. The acceleration just how fast is the velocity changing. And so if the rope broke, the climber would fall at 9.8 meters per second squared, and therefore that's not good for the climber, right? I mean, they're suddenly speeding up much faster than they were when the rope was actually helping them out. Okay, so problem here is because we know some information, but we still need to find the tension. So we know that net force equals mass times acceleration. We know the mass of the climber, and we know the acceleration of the climber, 1 meter per second squared, because fortunately the rope hasn't broke yet. We also know that the net force would be the weight minus the tension. The weight has to be greater than the tension because the climber is accelerating downward. If the tension was greater, the climber would be rising, right? So since the climber is accelerating downward, the tension has to be less than the weight. So if we subtract the tension from the weight, that's also the net force. So we know that the mass of the climber times their actual acceleration is equal to the weight of the climber, mg, minus tension force. And we know everything there except for the tension force. So now we can just solve for Ft. So the mass is 90. 60 was the last problem. And we know the acceleration is 1 meter per second squared. For mg, still 90 kilograms and 9.8 meters per second squared. And then the tension force is what we're solving for. So we can just isolate tension force and get our answer. Now, any questions on that before I go on to the next thing? All right. I want to show you an alternate approach. This what I've shown in green font here is what I would consider the logical approach or the conceptual approach. I know logically, if this person's accelerating down, their weight must be more than the tension. So I know I should subtract the tension from the weight. But for other problems, sometimes it gets a little confusing. Do I add? Do I subtract? Should this be positive? Should this be negative? Do I make 9.8 positive? Do I make it negative? What? There's a lot of questions that could come up if you're not real confident thinking through conceptually. So you can also take what I would call a vector approach. And when you take the vector approach, the benefit or the simplicity of it is you don't have to worry about whether you add or subtract, you always add. But you add them as vectors, so you have to make sure that the sign of every vector is included. So if we were going to solve this same problem with a vector approach, I would say that MA, the net force, equals mg, the weight, plus the tension. It's always plus. If I'm using a vector, I never subtract in terms of my setup. I might have to subtract to do an algebra step and solve for a variable, but I'm not going to, in my setup, I'm never going to subtract vectors. I'm always going to add them if I use the vector approach. But now I'm going to have to put all my numbers in as vectors, including their direction. So in this case, we set up above, the acceleration was downward. So we need to define, is down going to be positive or down going to be negative? So Rocky, what do you want to do? Do you want to say down is positive or down is negative?
Down is negative.
Okay, so we'll go with traditional. We're going to say, I'll just put it over here on the side, the upward direction is the positive direction. Okay, I'm just kind of reminding us, we're going to declare the norm here. Up is positive, down is negative. Okay, so now when we plug these in, mass is a scalar, so still just 90 kilograms. There is no plus or minus on a scalar because they're not directional. But the acceleration should be negative 1 meter per second squared because it told us the acceleration was downward, and Rocky said we're going to solve this one with down being negative. Now, if she had chosen the other way, we could still solve the problem. We would just make this positive. Okay, and then we've got m times g. Well, mass is still a scalar. It didn't change, so it's still 90 kilograms. But g now is due to gravitational force field of the Earth, which is going to pull down. So that is also going to be negative. If Rocky had chosen the other way and said, hey, let's make down positive. And now I'm still going to solve for the tension force. And what it ends up doing is I've got this negative 90 over here on the left, and I've got this negative something over here on the right. But to isolate the FT, I'm going to have to add this 90 times negative 9.8, that number. I'm going to have to add it to the other side. So I'm going to end up doing the same thing as I did here. I'm still going to be taking the weight minus the tension. But I didn't have to figure that out. It just, the math showed me because of the signs of my vectors. So some students prefer to think through the problems conceptually and not focus on the signs and the vectors. Other students get really confused about when you should add, when you subtract, and so they prefer to just go straight vector, and they always add, and they just decide to use vectors, signs for everything that is a vector. Both approaches are fine. Questions? I do highly recommend that whichever approach you choose for a particular problem, that you stick with that approach all the way through. I have seen often when students kind of decide they're going to switch in the middle of a problem and then they end up making a math error. So I would say if you're going to go conceptual, try to stay with it through the whole problem, or at least through that whole portion of that problem. And then if you're going to go vector, try to stick with that through the whole problem as well. All right, our last example is an Atwood machine. This is the simplest Atwood machine. It's just got a single pulley. It's got 2 weights. And it tells us here on this first slide, the tension in a rope is the same everywhere in the rope. If 2 masses hang down from either side of a cable, for instance, the tension in both sides must be the same. So you can see here, they're telling us the tension on the side of object 1 is the same as the tension on the side of object 2. Kyle, if I were to have this Atwood machine set up here in class and I was holding it so it didn't move, if I let go, which way would it spin? Would the pulley start spinning clockwise and have the 50-gram fall? Or would it start spinning counterclockwise and have the 50-gram rise?
It would spin clockwise.
Good. Yeah, so I mean, we can look at this and we logically know, hey, there's more weight on one side, so it's gonna, the 50 is gonna fall, the 20 is gonna rise, the pulley is gonna spin clockwise. I mean, there's no mystery. We would all predict the same thing. The question is, how do we solve a problem like this? So here are the multitude of things they could ask you to solve. If it were a free response, they would probably ask you to solve all of these things and maybe even some more. So we've got a 20 kilogram mass hanging from one end of the rope that passes over a small frictionless pulley. So like we said before, they'll usually mention that it's frictionless. A 50 kilogram weight is suspended from the other end of the rope. Find the tension in the rope. So the tension in the rope is the basic thing they want us to find. And you'll also notice they said that the pulley is small. That's basically saying we could ignore the mass of the pulley and the friction. All right. So these down here, A through F, are all of the different things that this curriculum is suggesting, the steps we take, suggesting how we would solve this problem and eventually figure out the tension. But first, before we look at those steps, which way will the 20 kilogram mass accelerate? See Nat pointing up, good. Which way will the 50 kilogram mass accelerate? Down, okay, good. The first thing we're gonna do is draw free body diagrams for each mass, and that's the key on a Atwood machine is, at times at least, you need to think about each side separately. Write the net force equation for each, find the equations for tension force, find the equation for the acceleration, find the value for the acceleration, and then find the value for the tension force. Now, if you remember the example we went through before break, you may remember my approach and our textbook approach of considering it as a system. But I want to show you an alternate approach today, and then I'll go back to the system one to remind you about that. So here's how this curriculum suggests to solve it. They take a very algebraic system of equations approach. So the first step they say is draw a free body diagram for each mass. And so over here on the left, you can see they've got the 20 kilogram object. It has its weight pulling down. It has a larger tension force pulling up. We know it's larger because this is going to rise. And then they have drawn on the right the free body diagram for the 50 kilogram mass. They know it's going to accelerate downwards, so the weight has to be larger than the tension force. And then, like we said before, these two tension forces are equal. So that's kind of the connecting thing. They have the same tension force. Different weights, same tension. All right. Will their acceleration have the same magnitude, or will they have different accelerations?
Be the same acceleration.
Yeah, they're connected. So if one moves, the other one has to move. If one accelerates, the other one has to accelerate. Their direction will be different, but one can't move faster than the other. Whatever one moves at, the other has to move at the same rate. Okay, so because they're connected, they will have the same acceleration. All right, let's move forward then. Write the net force equation for each mass. Remember, there's no special equation for tension. We need to use net force to find the tension. Below each diagram, write the net force equation for each one. Well, for each one, we know net force is ma. Like we know the base Newton's second law. Net force is ma. But let's think about that net force as a relationship for these. So let's start with the green one here. What's bigger, the weight or the tension? For the green one, for the 20 kilogram. Evan, what do you think? What's bigger, the tension or the weight for this green one?
The tension.
The tension. It's going to be pulled up, so that tension force must be greater than the weight. Because it was a rest. For it to go from rest to moving, there has to be a force to accelerate it upward. And so the tension force is greater, so we can say the net would be the tension force minus the weight force. Or let's just go ahead and say M1G. How about the blue one over here on the right? Sally, what do you think about this blue one on the right? What's going to be bigger, the weight force or the tension?
The weight force.
The weight force. It's going to accelerate down, so the downward force has to be bigger. So we would say m2g minus the tension. So I'm not taking a vector approach here. I'm taking just a conceptual approach, thinking it through. Questions about those two equations? All right. Here's the next step. So now they're going to do what we've been doing quite often. We know Newton's second law says the net force is equal to the mass times the acceleration. And then we already just said, well, that net force is also the tension minus the weight for the green one. And then for the blue one, the net force is mass times acceleration, Newton's second law. And as we said, that net force is also the weight minus the tension. Now, they just wrote it as negative tension plus the weight, as opposed to weight minus tension like we did, just so that the two tensions both come at the beginning of the equation. Now, I want you to notice something, though. One of the things that sometimes gets students a little bit tripped up with this scenario, to solve your systems this way, notice that they have said this one has an upward positive acceleration and this one has a downward positive acceleration. So they're switching the signs on either side of the pulley. And you kind of have to do that if you want to use this manner of algebra system approach, like the system of equations approach. That's another thing I think sometimes makes this a little less intuitive for students. Let's keep moving so you can kind of see. I think so far the steps, probably not too hard to follow. All right, so now we're just going to do some algebra. We have two equations, we have two unknowns, so we can combine the equations together and solve. So here we can see our two equations we came up with on the previous page. We solve this one for ft, so it is m1g plus m1a. We solve this one for ft, it is m2g minus m2a. And if they're both equal to ft, this one's ft, this one's ft, then we can just set them equal to each other. Now, that's basically how we solve systems, or one way we can solve systems of equations, right? So now we've got m1g, we know both of those things, plus m1a, we know both of those things. We don't know the acceleration, but we know the mass, equals m2g, we know both of those things, minus m2a. The only thing we don't know is a. And we said earlier, they should accelerate the same. So that whatever that a value is, those are going to be equal. So the next step then algebraically would be to get those a's together, to get those variables for acceleration together. So this slide is just showing you the algebra to do that. Here is what we had on the previous slide. We move this over and move that way, just using algebra. So we're just switching the sides of things so that now these two accelerations are on the same side of the equal sign. Then we factor out the a, and then we divide by m1 plus m2, and we come up with this equation. Now we can find the acceleration. Once we can find the acceleration, then we can figure out what that tension force is. So it's not, to me, a super straightforward process. It's quite a few equations, quite a few relationships. Got to think about the signs a little bit differently, but it works. And in the end, it comes up with really the same conclusion we're going to draw with the systems approach. And if you really like algebraic systems, I guess the benefit of this is you could have a lot of different problems with a lot of variety. And if you're really comfortable with systems of equations, it might make it easier for you to have just that same approach all the time instead of having to logically think through every question separately. All right, so here was the acceleration equation we came up with. Here is how they have plugged in the numbers, and they come up with an acceleration of 4.2 meters per second squared. They just plugged in the masses, plugged in the value for g, and they've got the acceleration, 4.2. Now, that is not how our textbook taught it, and that's not how we reviewed it before Christmas. So I'm going to quickly go back and show you how we did it before Christmas, which should take about 1 minute, a lot less than those 5 or 6 slides that this approach took for this particular problem. Now, it took a lot of slides because it's the first time you've seen it, so they're trying to break it down little by little. But I think the system approach at least for my brain and the way my brain processes math, is a little more direct. So I've highlighted this system approach here. Whoops. Go back. There we go. I've highlighted this system approach here, and this is just how I tend to solve the problems. So remember that the acceleration for both M1 and M2 is going to be the same. And so if we think about the net force being the total mass, so I have MT equals total mass. So the net force would be the total mass, the 20 plus the 50, times whatever that acceleration is. And the net force would also be the weight of M2, this one, minus the weight of M1, this one, because the 50 kilograms is going to pull down and the 20 is going to rise up. So that's the way I would subtract. All right, so if I put those two equations together, the total mass times acceleration equals M2, the weight force of M2 and the weight force of M1. I know the mass total is 70 kilograms. I can find the weight of the second one, 50 times 9.8, which gives me 490. I can find the weight of the first one, 20 times 9.8 is 196. And I solve for A, and I get the same thing we got in the previous slide. So to me, thinking about it as a system and using the total mass makes a little more sense and simplifies the math we have to do to come up with the same result, 4.2 meters per second squared. Your choice on how you want to solve it. Both methods always work. All right, now we haven't actually finished the question though. The final thing they wanted us to figure out was the tension. All we did is figure out the acceleration, which we needed to. You have to know the acceleration so you can figure out the tension, but we had to find this first. So now let's go ahead and find the tension, our final step. So the final tension, we want to focus on one box at a time. So if we focus on box A here in blue font, I've got the net force equals the tension minus the weight. The tension is going to be bigger than the weight because that 20 kilogram box is going to rise. The net force would be MA. The tension force is what we're looking for, and the weight force would be mg. If I plug those numbers in, m is 20 kilograms. We just found the acceleration is 4.2 meters per second squared. The weight is 20 times 9.8, so we can solve for the tension force, and we get 280 newtons. So the tension force actually is 280 newtons, and that's why that's on both boxes. Now, we could also solve it using the green box. For the green box, the net force would be the weight minus the tension, because the weight is greater than the tension. The weight would be mg, and so we know m, we know a, we know m, we know g. So all we have to do is solve for ft. The mass is 50 kilograms. Its actual acceleration is 4.2 meters per second squared. Its weight would be 50 kilograms times acceleration due to gravity. And if I solve for the tension force that way, I still get 280. It doesn't matter which one you choose. Both give you the same result. All right, any questions about Atwood machines or tension force or anything we've covered today? All right, let me give you some final instructions and get you in your breakout groups to do this Atwood machine group project. So like I said, it's going to be a gizmo on the Explore Learning website, just like the determining a spring constant gizmo was that's due tonight. You're going to be in groups of 2 or 3. Only one student needs to turn in a student exploration sheet. And so you'll probably all want to kind of be filling it in as you go. But as you're working today, you may want to start to talk about, hey, which one of us is going to be responsible for turning it in? It's not due till Thursday because you won't have time. We got about a little more than 25 minutes, but that's not going to probably be enough time for anyone to finish. In fact, you probably only get through a couple of pages in 25 minutes by the time you get to the site, download the paper, and do all that stuff. So on Thursday, I'm going to do a real quick review of a couple things at the beginning. And then you're going to have probably at least 70 minutes of the 80-minute class period Wednesday to continue working on this. And then if you finish early, you'll be able to work on the positive physics assignment Thursday. So Thursday's class will be almost entirely work time. So today is to get you started with your group. Yeah, Cade, if you're not able to see it, hopefully if you can on your phone follow along with your group, they may be able to share their screen with you so you can kind of follow along at least, even if you can't actually go to the Gizmo site yourself today, Cade. And then hopefully your power will come back on and you can get that document later. Appreciate you doing what you can to participate. All right, any questions about what to do? All right. Let me go ahead and get you into groups in. All right. I'm gonna make sure, Cade, you're in one of the groups of 3 so that you can have a better shot at sharing the screen. All right, so I'm just moving a couple groups around here. All right, good. Everybody know what to do? If you need help, call for help with the button on your group, and I'll come around and check on you a little bit later. Off you go.